In this video, we are going to discuss two important reactions on photochemistry. The first one, it is Paterno-Bucci. The second one, dipymethane rearrangement. Both the reactions, they are almost same, but there is little bit change in the substrate. Let us try to understand what is the difference. The first one, a ketone or aldehyde reacts with alkene. I have taken this to give oxetane. So basically it looks like 2 plus 2 cycloaddition. So this hydrogen is here. So even though it looks like 2 plus 2 cycloaddition, basically it is a radical reaction. Under photolytic condition, it undergoes Paterno-Bucci reaction to give oxetane. This compound, it is known as oxetane. If it is 3-membered, that is oxirane or epoxide. If it is 5-membered, then it is called tetrahydrofuran. If it is 6-membered, pyrene. So it goes like that. If it is 4-membered, we call it oxetane. What about dipymethane rearrangement? The dipymethane refers to this. Di, it is 2. Pi, it refers to pi bond. So basically it is pi bond. There are 2 pi bonds. So you can see here 2 pi bonds attached to methane. So this moiety, it is methane. So in methane, basically it is CH4. In that, 2 hydrogens are replaced with pi bond. So that is with alkene. So that is dipymethane compound. When this is subjected to photolysis, what will happen? So initially, what we get is an intermediate like this. If you compare the mechanism between this and this, in this case also we will get this intermediate. But that will be intermolecular between 2 molecules. But here it is within molecule. Now, in this case, this will form a 4-membered ring. But here, if it forms a 4-membered ring, there will be ring stain. This is 4-membered, another one 3-membered. Let us go for this dipymethane rearrangement. So this is dipymethane. Under photolytic condition, what we get is a compound like this, vinyl cyclopropane. First I go for Paterno-Bucci. Consider an aldehyde like this and alkene like this. So when it is subjected to photolysis, this double bond forms radical like this. Similarly, this double bond also forms radical. Now I have to connect this. Now this and this radical combines, this and this radical combines to form oxetane. What about the stereochemistry? In this, R and R dash, they are trans. The product also R and R dash will be trans. The second one, what about the Regis selectivity? Is it possible to attach this oxygen radical with this carbon? No. Initially, this is less substituted radical. So this combines with another less substituted radical to form a bond. So this and this, they are mono-substituted. So in other words, this is secondary radical, this one O radical. So they are reacting first. But this one, it is secondary and here it is tertiary. So these two are somewhat more stable compared to these two radicals. So they will react after some time. So because of that, we get only this compound. So the stability of radical decides the Regis selectivity. So what about methane rearrangement? I go for this compound. In this case also, they form radical like this. Now, these two combines to give biradical like this. Now, this also can combine. These two radicals also may combine to give a bicyclic compound. But if it forms a bond, then the compound will be like this. 4-membered and 3-membered. So the ring strain will be very high. So this reaction is not preferred. In order to remove this ring strain, what it does, it opens up the ring. So this falls here and this 3-membered ring is getting opened up to give this radical. This radical and one radical from this bond forms this double bond. Now there is no ring, so it is free to rotate. So this radical and this radical combines to give this product, that is vinite cyclopropane. You can try what will be the product in this case. If it undergoes the rearrangement, what will happen? Initially, we get like this, then this bond will be broken up. So what we get is so this forms a bond to give the product. So like this, you can try the reaction in several substrates and then you can appreciate the mechanism and the reaction.